Thank you very much. Good morning, everybody. My name is Daniel Neider, and I'm happy to have the opportunity to present our work on using machine learning for synthesizing invariants and contracts. And this work is actually an extension of an earlier framework called ICE learning. It came about in the realization that ICE learning is not so well suited if you want to do modular verification or if you want to synthesize contracts for recursive programs or concurrent programs. So this work is joint work with a bunch of people, namely Ezzeddin and Deepak D'Souza from the Indian Institute of Science, Pranav Garg from Amazon Research, and Madhusudan from the University of Illinois at Urbana-Champaign. So I think most of you are familiar with the concept of verification, but let me still walk you through some of the main ideas. So I'd like to think of verification as a reachability problem in a typically infinite graph. So suppose your system or your program is given as a graph where the vertices are the program configurations, right? So they describe the values of your variables and the location in the code your program is currently executing. Moreover, the edges in this graph correspond to the semantic, and that is how the program evolves from one configuration to the next. Now, suppose you're given a set of initial configurations in which your program starts, right? So typically the precondition, and a set of bad configurations which you would like to avoid because there is some assertion violated or some exception is thrown, right? Now, your program is buggy if there exists some path in this graph leading from an initial configuration to a bad configuration. And verification is all about proving that no such erroneous execution exists. And one very popular mechanism or technique to do that is to provide an inductive invariant. Right? So an inductive invariant is simply a subset of the program configurations that satisfies three properties. It has to include all the initial configurations, it has to exclude all the bad configurations, and it needs to be inductive. And inductive means if you look at some configuration in your invariant and you look at its successor configurations, then all these successor configurations need to be in the invariant as well, right? And then a straightforward induction, of course, shows that if you start in the initial configurations, you will never leave the invariant, and therefore no execution will ever reach a bad state. Okay. Now, in general, of course, it's undecidable whether such an inductive invariant exists. But because it's an important problem, various techniques for automatically inferring these types of invariants have been proposed. So, for instance, abstract interpretation, predicate abstraction, interpolation, and IC3-based methods. And recently, also learning-based approaches have emerged, including our own ICE learning framework. And as I said, this ICE learning framework is not very well suited for doing modular verification or inferring contracts of recursive functions. And the reason is that this typically involves synthesizing pre and post conditions or invariants at multiple points in your program. And so it's very difficult to, in some sense, flatten out this problem into this kind of neat graph structure. And to approach this problem, we now have proposed this extension of ICE learning, which we call Horn ICE learning, which addresses exactly this problem. And this is what I'll show you in the first part of my presentation. In the second part of my presentation, I'll present you a new learning algorithm, which is based on learning decision trees, which operates in this Horn ICE setting, and whose task it is to infer an invariant or contract from data it gathers from the program. Right? And in the following, just for the sake of simplicity, I will focus on inferring invariants and just mention contracts a little later. Okay, so let's start with this Horn ICE learning framework. Essentially, this framework is just a feedback loop between two entities. So on the one hand, we have the teacher component, which is essentially a program verifier, right? Which can reason symbolically about the program. On the other hand, we have the learner or the learning algorithm, whose task it is to learn an inductive invariant in interaction with the teacher component. So more specifically, what will happen is the following. In every iteration, the learner will propose some candidate invariant, some hypothesis, which can be an arbitrary subset of the program configurations. The teacher would take this hypothesis and check whether it's an inductive invariant. If this is true, then the learning stops, and we have found a correctness proof of our program. But if the teacher cannot prove the program correct, then it is required to extract what we call a counterexample. And this counterexample, intuitively, you should think of just as a witness as to why the hypothesis is not an inductive invariant. And then, of course, this loop continues until at some point the learner proposes an inductive invariant. Okay, so let me make this notion of counterexample a bit more precise. And in order to do so, I'd like to go back to our original ICE learning setting, which operates in the same, operates according to the same idea. So recall that the task of the teacher is, given some hypothesis, it needs to check whether it's an inductive invariant. And in order to do so, it just checks these three properties here, right? And whenever one is violated, it needs to reply some sort of counterexample. So suppose that the first condition is violated, right? So in this case, there exists some initial configuration C, which does not belong to our hypothesis. And the teacher would now extract such a configuration and return it as a so-called positive counterexample. And the meaning of this counterexample is any future hypothesis needs to include this positive counterexample, because we know that every inductive invariant has to include all the initial configurations. Similarly, it can happen that the learner proposes something which has a non-empty intersection with the set of bad configurations, in which case the teacher would reply with a negative counterexample. And the meaning is similar. It says that any future hypothesis has to exclude this negative counterexample. And then finally, it might happen that the hypothesis is not inductive, in which case there exists a program configuration C and a successor C prime, such that C belongs to the invariant, but C prime does not. Right? Now, in this situation, the teacher is somewhat stuck. So it doesn't know an invariant, right? I mean, the whole point is learning an invariant. So it would not know whether to exclude C prime or include C in order to fix this problem. Right? And the idea of ICE learning here is that we allow the teacher to reply with an implication counterexample, which is essentially this pair C prime. And its meaning is that if a future hypothesis includes C, it has to include C prime as well. And so in some sense, we are delegating this decision from the teacher part to the learner part. Now, if you want to do, let's say, modular verification, and then, as I said, it's not so easy to represent this problem in this nice kind of like flattened graph structure. And what typically happens is that implications are no longer sufficient to refute non-inductive hypotheses. So in general, counterexamples to inductivity are of a little bit more complex form, namely in form of these Horn constraints. Right? And the Horn constraint it's very similar to an implication, except that on the left-hand side there can be a conjunction of several program configurations. Right? And of course, an implication is just a special case where the left-hand side just contains a single configuration. Okay, so these Horn constraints are now the basic building blocks of our Horn ICE learning framework. Right? It's again this feedback loop between the teacher and the learner, and we now have positive, negative, and these Horn counterexamples. Okay, now in all of these learning-based verification techniques, so typically all of them share this nice property that you can very often simply reuse existing verification infrastructure to build the teacher component, right? So pick your favorite program verifier, and then it's typically enough to add a little bit of boilerplate code to read in candidates and to extract counterexamples if your verification fails. Right? And for this reason, I do not want to talk about this teacher component, but I'd rather focus on the learner part here. So in general, what the learning algorithm would do is the following. So it would maintain some data structure, which we call a sample, in which it collects all the counterexamples it receives from the teacher. Right? And in every iteration, it would produce a hypothesis that is consistent with this information, meaning that it includes all the positive counterexamples, it includes all the negative counterexamples, and it respects the Horn counterexample. Okay, so this is the general case, and now let me show you how to build such a learning algorithm that operates in this Horn ICE learning framework using learning algorithm for decision trees. Right. So this is the hello world example for decision trees. So suppose we want to know whether we play tennis depending on how the weather is outside. Right? And let's say we want to make our decision dependent on whether it's sunny or hot or windy. And then the decision tree simply is this tree-like structure where in the inner nodes you have these predicates, whether it's sunny, hot, or windy, right? And in the leaf nodes, you have the decision whether you play tennis or not. So here you play tennis, and here you don't play tennis. Right? Now, if you want to know whether to play tennis, you start at the root. You check whether it's sunny. If it's sunny, you follow the solid line, and you immediately play. If it's not sunny, you follow the dashed line and check whether it's windy. If it's windy, you follow again the solid line and you don't play. If it's not windy, you follow the dashed line and you play. Okay? Very simple. Now, a decision tree learning algorithm would now take such a table here, right, and generate a decision tree out of it. Right? And the idea, or how it would try to do this in a way that it minimizes the size of this tree in the sense that it has as few of these decisions as possible. And the idea is that, you know, if you have a very large tree, it's essentially just encoding a large if-then-else expression over your data, right? And this is something you don't want to have. Rather, you have some succinct rule. The nice thing about these decision tree learning algorithms is they don't care about what your predicates are, right? And so our idea here is instead of using sunny, hot, and windy, we just use predicates over our program configurations. Okay? And this turns this decision tree into some symbolic representation of a set of program configurations. And this is what we will propose as the hypothesis to our teacher component and how we represent our inductive invariants. All right, so typically, of course, you cannot just give this tree to your program verifier, but you have to bring it in a somewhat nicer form. So for instance, into some logical formula over the predicates you have chosen. Right, some Boolean formula over the predicates you've chosen. And the nice thing about these decision trees is that they're actually just another representation of a formula in a disjunctive normal form. Right? So for instance here, this tree corresponds to this formula here. It says, you know, f x is greater or equal to 0, right? Which leads you to this, you know, positive leaf node, or not x is greater or equal to 0, and not x is smaller or equal to result. Okay. So now the question, of course, is how does this decision tree learning work, and how do we handle implications? And in order to do this, I'd like to illustrate this with a simple example here. So suppose we're given this sample, and for the sake of simplicity, let's say we have just very simple horn constraints, which are in the form of implications. Right? Remember that these the configurations that occur in these horn constraints here, these endpoints, they don't carry a label, a classification, and our algorithm has to assign one in accordance with the constraints that are encoded by these implications. Okay? Now the idea is the following. So we pick some predicate and split our initial sample into two subsamples, one containing all the configurations satisfying the predicate and one that contain all that do not satisfy this predicate. Right? Now it's of course important which predicate here to choose, but in order to save some time, I can't go into details here, and I need to refer you to our paper, or you can ask me later if you like. Now the idea is that this, of course, creates our first decision node in the tree, and then we just recurse. We pick one sample, we split, and we continue until we arrive at some subsamples which are pure in the sense that they only contain configurations of a certain type, either positive or negative, or these kind of unclassified endpoints of implication. And at this point, we would like to turn these samples into leaf nodes of our tree. So let's say we pick this one here and turn it into a positive leaf node, right? Because all the configurations that are in here and carry a classification are positive. So what we'll do is we, turn all classifications that occur in endpoints of implications to positive. But in order to satisfy this constraint, we have to, because now the left-hand side is true, we have to propagate this information to the right-hand side as well. Right? So we turn this into a positive node as well. Note that this is okay because we have not yet touched this sample over here. So whenever our algorithm will arrive at this node, we can take care of the information we've just changed. Right? And similarly, if you want to turn this into a negative node, you have to propagate this information backwards along the implication. Right? And then we continue until we have constructed or completed the tree construction. All right. Now, Horn constraints are a bit more complicated to handle, of course. And this is because of two things. So the first observation here is that if you just change, let's say, a few of these configurations that occur in these Horn constraints, you're not immediately triggering this information propagation. Right? So these still can be unclassified here. But this is actually a good thing because it leaves room to the learning algorithm down the line. So when the learning algorithm at some point later in the tree construction, arrives at, let's say, this configuration, it can still decide whether to put it positive or negative. So this is a good thing. This doesn't cause any problems. More complicated is the case, or it's more complicated if you have a lot of these Horn constraints, and typically they depend on each other in a very intricate way, right? And so it's not clear whether, let's say, you want to put this positive, whether this still results in some system of Horn constraints which is still satisfiable. And in order to check this, we came up with a new solver for Horn clauses. So essentially, you can take any solver for Horn clauses to check this property. Though these classical Horn solvers, they tend to assign a value to all the variables involved in these Horn constraints, right? And if you remember what I said here, this is a property we would not like to have. And so our Horn solver really only fixes the minimal number of configurations or variables that are forced to be true or false. And the second property is that it works incrementally. And this is because we have to call the solver every time we want to check whether we can create a leaf node or not. So it's a good thing to have this in an incremental way. OK, so in the interest of time, maybe let's do this quickly here. This lemma simply states that if your sample is non-contradictory and you have sufficiently many of those predicates, then our algorithm is guaranteed to produce something which is consistent, which is a nice thing. So this means that one iteration in our loop does essentially the right stuff, right? It's a consistent learning algorithm. More interesting might be this theorem here. And this one says that by exploiting some subtle properties of our learning algorithm and adding additional Horn constraints in a smart manner, we can even guarantee that this overall feedback loop will at some point converge to an inductive invariant if there exists one that can be expressed as a decision tree over our chosen set of predicates. And this is, of course, a very nice and a very strong theoretical result. The question is, how does this perform in practice? And so the last slide, I just want to show you one experimental evaluation. We have more in our paper, which is on recursive programs. And we have taken this benchmark set from the software verification competition track on recursive programs. We have compared our implementation, which is on top of the Microsoft Booby program verifier, with Ultimate Automizer. And Ultimate Automizer is the winner of this year's software verification track. So it's essentially the strongest verifier that can handle these recursive programs. And let me just briefly tell you how to read this scatter plot here. So the idea is that every benchmark corresponds to one of those dots. And dots above the diagonal are benchmarks in which our tool performs better than Automizer. And below the diagonal, there are these benchmarks in which Automizer performs better. As you can see, we can roughly verify the same number of benchmarks. But for most of the benchmarks, we are roughly one order of magnitude faster than Ultimate Automizer. And this is, of course, also a very promising result here because our tool is also not very polished yet. And this is what we're currently doing. We're polishing it up, and we want to submit it to next year's software verification competition. All right. So, and with this, I'd like to conclude. There are many more things in the paper I could not talk about. So, for instance, there are these many heuristics, how to choose predicates and which node to expand, and these kind of small, nasty things that make this thing work or not. You can read more of them in the paper. There's more experimental evaluation on sequential and concurrent programs. And I'd also like you to point to our implementation, which you can either find on GitHub or in the ACM digital library. And yeah, with this, thank you for your attention. I'm happy to take questions.
Any questions? Thank you for the talk. On this graph on with the performance, it seems that most of the time you are better than the automizer, but
Right.
in that rare times when you're worse, you have like you are behind quite a bit, right?
Right.
So do you see any path to improvement in these cases?
So actually, debugging these decision tree learners is a difficult thing because there are a lot of heuristics which have some intricate interplay with each other. And actually, we had several ideas of what heuristics to choose and which to take and so on. And at some point, I think we had more than, I don't know, like hundreds of possible combinations what we could choose. And at some point, we just settled for one which produced this result. But it's true that we currently don't very well understand what the interplay between these heuristics and so forth is. And it's definitely an interesting thing to figure out why certain configurations work better. And yeah, of course, try to make these things work. I'll move over here. Yes.
Thank you.
No questions? Maybe we can have one more question. Okay, so let's thank both the speakers.